Now we talk about principle of work and energy. Now the very simple three concept we're going to take it. Now let's talk about principle of work energy. What is it based on? It is based on conservation of energy. Now what is this conservation of energy is telling us? Is telling me that work done by external force, so work done by external force. So for example, if let's say I take the one cube, and if some force is applied, then this cube going to move at some distance delta, so that is external work done. So external work done in this case is P times delta. Let's say W is external work done, or we can say that external work done UE is P delta, load times how much distance is moving. So work done by this is transfer into internal work. So external work transfer into internal work, and that internal work is strain energy, right? We take strain energy before, and that is stored, and that is UI. So what is telling us that once you have let's say this is the some surface, and if I apply the load on this cube, then it will displace by delta. So what this says that the external work done, which is P delta, that will be equal to the internal stored. So how much it's going to store, that we have a different scenario for different cases, that we have taken different we take two example to calculate the internal energy. So that's telling me that external work done is stored into that any body is UI. Now let's take the truss. Let's take the case for the truss, and we're going to center about these principles. Let's take about truss. So let's say one truss is a very simple truss. Let's say for examples we have this truss system here. In this case, if I apply the load here, and let's say for example if this one is pin support, this one is roller support, and then this truss will have some displacement in that direction of load. So let's say for example this beam will have a displacement in this fashion, and this all uniformly they will disturb. So let's say this is my delta. Okay, now we are interested to find this delta. What is this delta under this loading? So how can we find? We use this external work done is equal to internal work done. For the case of external work done, 1/2 P delta, we take this video to calculate external work done, and internal work done would be sum of all the forces over L times L over 2EA. Okay, so whatever the number of members, let's say this is I, so I and I, so 1 2 3 4, we take the examples to calculate this one. So in here we can find delta. We can just put this P across and 1/2 across, you can find the delta for truss. Now if someone give you the beam, and if you want to find the, let's say, simply supported beam, and let's say it has applied the load P, in that case it will have some deflection here, delta. To find the deflections, we can use the same principles, 1/2 P delta, and we also calculate the internal energy in this case as well. Let's say this is external energy and this is internal energy. So we can find this delta is equal to, let's say, 2 and over P 0 to L m square on 2 EI delta x. So we can find this deflection in the beam using this principle. And let's say for example we have this cantilever beam, and we apply the concentric moment at this point, and if you want to find in that case the rotation, so 1/2 m theta, this m is this one, equal to 0 to L. We have strain energy equation for moment, and we can solve for theta. That theta is the rotations is when you have this beam, and that theta is the angle of that slope of that tangent or that particular point. So that is a rotation or slope. So we can find the deflection using this principle: external load equal to internal load or internal energy, and we can take some example to solve the deflections. Thank you.